Okay, so we are going to finish our discussion on amines today, and we are going to focus on the physical properties and why amines are basic and how do we characterize that basicity. I'm sure you're all familiar with the smell of ammonia. It's very sharp and pungent. So like the smell of ammonia, our low molecular weight amines also have that same odor. Trimethylamine, obviously, which is one amine, NH2, with 3 methyl groups attached to it, is considered a tertiary amine, has a smell of rotting fish. 2 other particularly pungent amines are 1,4-butadiene, which is called putrescine, and 1,5-pentanediamine, which is called cadaverine. And both of these amines are associated with the decomposition of human bodies, and I'm sure other dead things as well. Just to talk about the structure a little bit, the first one is a 4-carbon chain with an amine group on the first and fourth, and then the second one is a 5-carbon chain with an amine group on the first and fifth. Amines are polar compounds. You should remember this because in the bonding unit we learned that hydrogen bonds exist when hydrogen forms a bond with NOF, nitrogen, oxygen, or fluorine. Both first and secondary amines will have the hydrogen bonds. The tertiary amines can have no hydrogen bonds because all of their bond sites are filled. You have an amine, and remember, nitrogen can only form 3 bonds because it has 5 valence electrons, and each of those bond sites are inhabited by another carbon from the methyl groups. Let's talk about some physical properties. A nitrogen-hydrogen-nitrogen hydrogen bond is weaker than an oxygen-hydrogen-oxygen bond. And we can tell this by looking at the electronegativity difference between the N and the H and the O and the H. And remember, you always have your electronegativity tables on your reference sheets. Some of you forgot to use them on the last exam. So let's look at the difference in the molecular weight and the boiling point. We did this when we talked about alcohols. Remember that smaller alcohols have a lower melting and boiling point than high chain alcohols. Here you see the difference between CH3CH3, CH3NH2, and CH3OH. So here you just have ethene, right, which is an alkene. This is a nonpolar molecule, as opposed to methylamine, which has an amine group, and then methanol, which is an alcohol. And you can see the molecular weight and you can see the boiling point. This should make sense to you because we know that nonpolar molecules have London dispersion forces, therefore they're going to have weaker forces and a lower boiling point. The amines, as we just said, have a weaker hydrogen bond than the alcohols, which is really evidenced by the boiling point with the strong hydrogen bonds in the OH. Now, if we're just comparing amines, they will form, as I said, primary and secondary amines, hydrogen bonds with water. And they are more soluble in water than just regular hydrocarbons of comparable molecular weight, as you just saw, because most hydrocarbons, which is just hydrogen and carbon, are nonpolar molecules. Most low molecular amines are completely soluble in water, like alcohols. Higher molecular amines are only moderately soluble in water or insoluble. Why? Because you wind up having that long non-polar end. So if we can look at, let's just look at an alcohol, a 3-carbon alcohol versus a 6-carbon alcohol. So the top one is going to be more soluble in water than the bottom one. Why? In the bottom one, you have this long non-polar tail, right? These are all London dispersion forces here. So it's not going to make it very conducive for dissolving. It's going to be the same thing with your amines. If I were to take off my OH and put NH2 on the end here, it's going to be the same thing. The top molecule is going to be more soluble than the bottom one for the same reason. But when comparing amines to alcohols, your alcohols will be more soluble than your amines. Like ammonia, amines are weak bases, and aqueous solutions of amines are basic, meaning amines in water. The acid-base reaction between an amine and water involves a transfer of a proton from water to the amine. So here you can see we have methylamine, and what winds up happening is water acts as the acid here and transfers a hydrogen to the methylamine, forming methyl ammonium hydroxide. And the reason why it's considered methyl ammonium hydroxide is because you still have the OH minus in solution with it. In a previous unit, we talked about Ka and pKa. pKa being the negative log of the Ka, and that was the acid dissociation constant. We're now going to look at the base dissociation constant for a reaction of an amine with water. So we just wrote this reaction on the previous page. Remember, when we write the dissociation constant, it's always the products over the reactants. So the methyl ammonium hydroxide was the product, and the methylamine was a reactant. We never include actual water in the equation. So here the Kb for that is 4.37 times 10 to the negative 4, and if we take the negative log, we get the pKb. Aliphatic amines have about the same base strength and are slightly stronger than ammonia. Remember, aliphatic amines are our straight chain amines. Aromatic and heterocyclic aromatic amines are considerably weaker bases than aliphatic amines. I'm sorry the way this copied. You can't see what it says underneath. It says, note that while aliphatic amines are weak bases, by comparison with inorganic bases such as sodium hydroxide, they are strong bases among organic compounds. So they're not strong like sodium hydroxide. They're considered weak bases when compared to something strong like sodium hydroxide. But if you're looking just at organic compounds, right, because sodium hydroxide is considered ionic. where organic compounds are simply covalent, it's considered strong. Given the basic nature of amines, we can determine which form of an amine exists in body fluids. For example, blood. We know that in a normal healthy person, blood is slightly basic, around 7.4. If an aliphatic amine is dissolved in the blood, it's predominantly in its protonated or conjugated acid form, because when in the blood you have water, so the water is going to donate an H to the amine, let's say dopamine, and in the blood it's present in the acidic form. In this example, we're going to assume that the amine RNH2, and R meaning some variable that's particular to the amine, has a pKb of 3.5, and that it is dissolved in blood, which has a pH of 7.4. For this to work, you have to make sure that your pKb agrees with a pOH. When we use pH, we would use pKa. So we find the pOH by taking 14 and subtracting 7.4. We've learned this before, and we get 6.6. So the first thing we do is we write our base dissociation constant. So that means that it's going to be Kb is equal to RNH3 plus times OH concentration over RNH2. So remember, that's the products over the reactants. What got hidden here is you have to remember that you actually need concentration. Those square brackets mean concentration. So we have to take our pOH of 6.6 and get it into a concentration. This was also on the last exam. So that's when you have to take the inverse log raised to the negative pH or pOH in this case. So you're going to do inverse log, right? Second log, and then you're going to do negative 6.6. And when you do that, you'll get a concentration of 2.5 times 10 to the negative 7. And to go from the pKb to the Kb, we're going to do the same thing. We're going to do inverse log raised to the negative 3.5, and then we get 3.2 times 10 to the negative 4. So remember what we're solving for. We're substituting in our Kb, because the Kb is equal to the RNH3 plus concentration times the OH minus concentration over the RNH2 concentration. So when we rearrange and we put in our Kb and OH into our concentration, we get 1300 as the ratio. What that number means is that 99.9% of the aliphatic amine is present in the conjugate acid form, meaning the RNH3 plus. The most important chemical property of amines is their basicity. Doesn't matter whether they're water soluble or not, they are going to react in a quantitative manner, meaning a measurable manner, with strong acids to form water-soluble salts. So here you can see norepinephrine, which is only slightly soluble in water. It's going to react with hydrochloric acid in the presence of water, and it's going to form norepinephrine hydrochloride. So what happens is the H is donated by the acid to form a water-soluble salt. And that's because it's got that negative charge on the Cl, which we know water is polar, and it likes to have those opposite charges attracted to the hydrogen end of the water molecule. So using the example that we just did on the previous page, remember you're going to add the HCl to this. So what you're forming is CH3, CH2, 2, and then NH2Cl. So this is diethyl, because this is an ethyl group, ammonium, because the NH2, chloride. So there is your salt. So let's finish up with some real-world examples. Amphetamine, methamphetamine, and phentermine are all synthetic amines, mean man-made. They're powerful stimulants of the central nervous system. Like most other amines, they are stored and administered as their salts. The sulfate salt of amphetamine is named benzodrine. The hydrochloric salt of the S enantiomer of methamphetamine is named methadrine, and the hydrochloride salt of phentermine is named fastin. First of all, you're going to hear enantiomer come up again in the future if you haven't read about it in this chapter. And all that means is that it's two molecules, there are mirror images of each other. So when you talk about the mirror image of methamphetamine, that's what they're talking about, the S enantiomer. So it's the mirror image of methamphetamine. So all three of these amines have similar physiological effects and are referred to by their general name of amphetamines. Structurally, though, they have in common the benzene ring with a 3-carbon side chain and an amine nitrogen on the second carbon of the side chain. Physiologically, they share an ability to reduce fatigue and diminish hunger by raising glucose level of the blood. Because of these properties, amphetamines are widely prescribed to counter mild depression, reduce hyperactivity in children, and suppress appetite in people who are trying to lose weight. These drugs are also used illegally to reduce fatigue and elevate mood. Abuse of amphetamines can have severe effects on both the body and the mind. They have an addictive nature, and they concentrate in the brain and central nervous system, which can lead to long periods of sleeplessness, loss of weight, and paranoia. The action of amphetamines is similar to that of epinephrine, the hydrochloride salt of which is named adrenaline. So these are the three amphetamines that we were just talking about. You can see that the amine group is on the second carbon of the chain, and what makes them different is actually the placement of the methyl group or groups. Another one that is important in this chapter are alkaloids, which are basic nitrogen-containing compounds. Again, here we go with the amines and the basicity. They're found in roots, bark, leaves, berries, or fruits of plants. In almost all alkaloids, the nitrogen atom is part of the ring. The name alkaloid was chosen because these compounds are alkali-like, meaning basic in nature, and they react with strong acids to give a water-soluble salt. We were just talking about that. Now, the difference between these and the amphetamines that we were just looking at is that here the nitrogen is actually part of the ring. Thousands of different alkaloids, many of which are used in modern medicine, have been extracted from plant sources. When administered to animals, including humans, alkaloids have pronounced physiological effects. They can have individual effects depending on the person or the animal, but most are toxic in large doses. And for some, that toxic dose can be very, very small. So every drug has its own LD50, so lethal dose, and that's the amount that it would take to kill 50% of the population. S-conine is the toxic principle of water hemlock, which is a member of the carrot family. Its ingestion can cause weakness, labored respiration, paralysis, and eventually death. It is a toxic substance in the poison hemlock used in the death of Socrates. Water hemlock is easily confused with Queen Anne's lace, which is a type of wild carrot, and that mistake has killed numerous people. S-nicotine, a different type of alkaloid, occurs in the tobacco plant. In small doses, it is an addictive stimulant. In larger doses, this substance causes depression, nausea, and vomiting. In still larger doses, it is a deadly poison. Solutions of nicotine in water are used as insecticides. And then cocaine is a central nervous system stimulant obtained from the leaves of the cocoa plant. And in small doses, it decreases fatigue and gives a sense of well-being. Prolonged use, though, as I'm sure you are well aware, can lead to physiological addiction and depression. And lastly, we're going to look at epinephrine. In this article in your textbook, they talk about a prototype that's used for the development of new bronchodilators. Epinephrine was first isolated in its pure form in 1897 and its structure determined in 1901. It occurs in the adrenal gland, hence the common name adrenaline. As a single enantiomer with the R configuration at its stereoisomer, epinephrine is commonly referred to as a catecholamine. The common name of 1,2-dihydroxybenzene is catechol, and amines containing benzene ring with an orthohydroxyl group are called catecholamines. And I think you did something in biology with the study of catecholamines. Early on, it was recognized that epinephrine is a vasoconstrictor and a bronchodilator and a cardiac stimulant. The fact that it has these three major effects stimulated much research, one line of which sought to develop compounds that are even more effective bronchodilators than epinephrine, but at the same time are free from epinephrine's cardiac stimulating and vasoconstricting effects. Soon after epinephrine became commercially available, it emerged as an important treatment of asthma and hay fever. It has been marketed for the relief of bronchospasms under several trade names, including Bronchade Mist and Primatene Mist. One of the most important of the first synthetic catecholamines was isoproterenol, the laboratory enantiomer of which retains the bronchodilating effects of epinephrine, but is free from the cardiac stimulating effects. This R-isoproterenol was introduced into clinical medicine in 1951, and for the next 2 decades, it was the drug of choice for the treatment of asthmatic attacks. Interesting, the hydrochloride salt of the S-isoproterenol is a nasal decongestant and was marketed under several trade names, including Sudafed. A problem with the first synthetic catecholamines and with epinephrine itself is that they are inactivated by the enzyme-catalyzed reaction that converts one of the two OH groups on the catechol unit to an OCH3 group. A strategy to circumvent this enzyme-catalyzed inactivation was to replace the catechol unit with one that would allow the drug to bind to the catecholamine receptors in the bronchi and would not be inactivated by this enzyme. In terbutaline, which is called breath air, inactivation is presented by placing the OH groups meta to each other, meaning next to each other, on an aromatic ring. In addition, the isopropyl group of isoproterenol is replaced with a tertiary butyl group. So all this has to do with is simply moving some things around in the structure. That's what all these big words are talking about. In addition, the isopropyl group of the isoproterenol is replaced, as I said, with the terse butyl group. In albuterol, which is Proventil, the commercially most successful of the anti-asthmatic medications, 1-OH group of the catechol unit is replaced with a CH2OH group, and the isopropyl group is replaced with a terse butyl group. When terbutaline and albuterol were introduced into clinical medicine in the 1960s, they almost immediately replaced isoproterenol as the drugs of choice for the treatment of asthmatic attacks. The R enantiomer of albuterol is 68 times more effective in the treatment of asthma than the S enantiomer. In their research for a longer-acting bronchodilator, scientists reasoned that extending the side chains on the nitrogen might strengthen the binding of the drug to the adrenoreceptors in the lungs, thereby increasing the duration of the drug's action. This line of reasoning led to synthesis and introduction of salmeterol, or Ceravent, a bronchodilator that is approximately 10 times more potent than albuterol and remains active for much longer. So here you can see how they change the structure around to make it more effective, and then the final structure of the salmeterol is with the increased length of the side chain. So when we talk about these drugs, there's so much research that's just being done with taking the same structure and just moving these functional groups to different locations and see how that affects the interaction of the drug. Sometimes it works, sometimes it doesn't. You can see here, through trial and error, they've been able to perfect the drug. And I'm sure that they're still doing research to even make it even more effective. Now, if they could just get the cost down, it would be a win-win for everybody. Okay, that ends chapter 16.